Okay, so this is lesson 2.5, and it's the quantum mechanical model. Specifically, it's comparing and contrasting the Bohr model to the quantum mechanical model as an introduction to the real model, the quantum mechanical model. So on the 2.5 Bohr model versus quantum mechanical model graphic organizer, we're going to compare Bohr and quantum. So you need to take notes on your worksheet from this video. So what you should do is pause right now, go to Schoology, find that worksheet, and download the worksheet so that you've got it on your screen. You can do a split screen, so you've got the video on one half and the worksheet on the other half, and you can take notes by typing into that worksheet. So in this video, you're going to see a table that looks just like that worksheet. So here's the first part of that table. If you haven't found the worksheet yet, again, pause right now, go to Schoology, find the 2.5 worksheet, download it into Word, open it up, and this is what you're going to see. It's going to say Bohr model and quantum model and show you a table that looks like this. So the words that are in black are already in your table. You're adding in what I've shown you here in red. So the Bohr model, it only works for hydrogen. Bohr did a lot of experiments, and he was able to calculate how much energy the electron has in hydrogen. It works when there's only one electron. So he could calculate exactly how much energy the electron had depending on which orbit it's in. He could see exactly how far it was from the nucleus. He could calculate all of that and work great. But as soon as he tried to do it for an element that had 2 or more electrons, it didn't work. The quantum mechanical model, on the other hand, works for all elements, works for everything. In the Bohr model, the electron is viewed as a particle, and this makes sense. We're looking at it as a small, very, very small mass. It's a teeny tiny particle. So we expect it to behave the way we would a particle in the real world. So a ball, a ping pong ball, a baseball, we know what this is going to look like. We know how it's going to behave if we throw it or roll it or something like that. So that's how we expect the electron to behave. But in the quantum mechanical model, the electron is viewed as both a particle and a wave. This is weird. This is strange. The idea that something that has mass could behave as a wave is kind of a strange idea. And this is the beginnings of the quantum mechanical model is a strange thing. It doesn't necessarily make a whole lot of sense. Some people have said, if you think that the quantum mechanical model makes sense, then you don't really understand what it's saying. Schrodinger, who's the person that really developed all the math for the model, kind of came up with the model. Years later, he said, nope, it's too strange, it's too crazy, I don't believe it. None of this is real, it can't be right. Everybody else still thought it was right, but he decided his own theory was crazy. So it's a very strange idea to say that the electron can behave as a particle, but can also behave as a wave. There are some experiments that it makes more sense to model an electron as a particle. You can explain what's going on that way. There's some experiments where it makes more sense to model the electron as a wave. And if you look at the electron as a particle, you can't explain what's going on. So it's a little bit of both. In the Bohr model, the orbits are 2-dimensional circles. Remember, Bohr drew circles around the nucleus, like planets orbiting the sun, the planetary model. He said we have these flat, 2-dimensional circular orbits, and we know exactly where the electron is. It's exactly this distance from the nucleus. In the quantum mechanical model, we don't call them orbits anymore. We call them orbitals. See how there's AL at the end of that? Orbital, orbital, orbit, orbit and orbital. So we're changing the name a little bit to try to make a differentiation between those 2-dimensional circles. Orbitals are 3-dimensional. They have many shapes, and together they form what we now call the electron cloud. So it's not as simple as just those 2-dimensional flat circles. So the idea of an electron cloud is that you could, for example, look at the propeller on this airplane. When that propeller spins, you know that the propeller blade is in there somewhere. You can see this blur. It's somewhere in that area. So you know that there's most likely a blade there in front of the plane. The blade is not a mile away from the plane. It's most probably going to be found somewhere in that blurred area. So that's kind of the idea with a cloud. The electron cloud is a visual representation of the probability of finding an electron in that area. We call it a cloud because a cloud has no definite edge. It doesn't just stop. A cloud instead just dissipates. It gets less and less dense. There are fewer and fewer water molecules making up that cloud. It just gets more and more thin until eventually it disappears. So with the electron cloud, the probability of finding an electron close to the nucleus is really high, but the further you get from the nucleus, that probability just dissipates. It decreases slowly. It gets less and less likely. So there's no definite hard edge where it just stops. It just slowly fades away, just like a cloud would. So Bohr said that the orbits are exact locations of the electron. He said that he could calculate the radius of that orbit and tell you exactly where the electron is located. Each orbit had a specific energy and specific distance from the nucleus. And he calculated all of that for hydrogen, but it only worked for hydrogen. As soon as he put 2 electrons in there, it stopped working. In the quantum model, however, orbitals are probability maps of where the electron is likely to be found. We don't try to say we can ever know exactly where the electron is. In fact, Heisenberg, who also contributed to this model, has the uncertainty principle. He said you can never know exactly where an electron is and how fast it's moving at the same time. You can only know one or the other. You can either know how fast it's going, or you can know where it is. So this is another one of those strange things about the way electrons behave. They sometimes behave like particles. They sometimes behave like waves. We can't know exactly where they are and how fast they're going at the same time. All we can know is where they're likely to be found, the probability of finding the electron, not its exact location. The orbitals themselves are derived from Schrödinger's wave equations. So he did a bunch of math. He did a lot of complicated math, and the solution to his complicated equations tell us the shape of the orbitals. They tell us where we're likely to find the electrons and how much energy they have in those different orbitals. Luckily, we don't have to solve Schrödinger's equations. We don't have to go through the math. We just use the results of the math. Now, both models, these 2 items are true for both models. We're not contrasting here. We're comparing. They're the same. So electrons can jump from one orbital to another by gaining or losing a quantum of energy. This is what we talked about in the previous lecture with the atomic spectra information. Bohr used the observation of atomic spectra to help him create his model. Part of his model said that electrons can jump up and down from one orbit or one orbital to another by gaining or losing energy. That idea hasn't changed. We're still using that in the quantum mechanical model. We still need to explain the atomic spectra, and this is how we're doing it, by modeling the electrons as able to jump up and down. So the energy of an electron increases as the electron moves further from the nucleus. The ground state is the electrons at their lowest possible energy level, and the excited state has electrons at higher energy levels. This is the way Bohr described it. This is still the way the quantum mechanical model describes it. Now we're back to contrasting again, things that are different between Bohr and quantum. So for the Bohr model, orbits are labeled by numbers, 1, 2, 3, 4, etc. So he just has circles. The circle closest to the nucleus is number 1, and you just number out from there. Very straightforward. Quantum mechanical model, however, is more complicated. First, we have a principal energy level, 1, 2, 3, 4. But that's not all. Those principal energy levels are subdivided into sublevels. Sublevels are called S, P, D, and F. So they're labeled with letters instead of with numbers. Now, when this first was invented, those letters meant something. They stood for something. But what they stood for really doesn't make any sense to us. It's not really relevant to us. So we're going to come up with something else for S, P, D, and F to stand for, and I'll show you that in a minute. For right now, just look at it as first we have a principal energy level, and then we just subdivide that into a sublevel. And then sublevels are once again subdivided because there's more than one orbital per sublevel. So the pattern gets a lot more complicated. The organization is a lot more complicated, which is why sometimes it's nice to go back to the Bohr model and just look at these simple circles, 1, 2, 3, 4. In our next lesson, you're going to start organizing the patterns of the principal energy level, the sublevel, and the orbital to try to kind of make sense of some of those patterns before we apply the chemistry to them. So you'll see more about that soon. And then my last one, I don't really have anything to put about Bohr in this last spot, but to say a little bit more about the quantum models. The sublevels have different shapes. The electron clouds have different shapes. So that's what we're going to do with these letters. We're going to say S stands for sphere, P stands for peanut, D stands for double peanut, and F stands for fan. So I'm going to show you pictures of all of these shapes so you can see what we're talking about. So there's a sphere, S for sphere. It's a spherical shape, pretty easy. P for peanut. So this means like a peanut still in the shell, like a roasted peanut. And there are 3 orbitals within the P sublevel. So I'm showing you all 3 of them here. There's 3 different P orbitals. Then we have D. There's 5 of these. So D for double peanut, meaning imagine that you take 2 peanuts and put them on top of each other. So the first 4 pictures look like that. The 5th picture, I don't know. I don't know what that looks like. So again, we're trying to describe a shape, but it's not a perfect thing here. So SPD, sphere peanut, double peanut, I learned that in high school. High school students all over the country are learning that right now. Now for the last one, F, my teacher never showed us F, and she never had a word for it. So over the years, my students have suggested different things. Most kids say it looks like a fan, or it looks like a flower. I've also heard Ferris wheel. So if you have a word that you think better describes this, and it starts with F, so you can remember that F relates to a shape, feel free to use your word. If you like one of these words, great, use that. Fan, flower, Ferris wheel, something to help you remember that the F sublevel has a different shape. You'll also notice here there are 7 orbitals here. So again, we have more orbitals subdividing this sublevel. So Bohr's model is really simple. It's easy to picture in your head what's going on. With this model, it's just not so easy. It's harder to imagine all of these levels and sublevels and orbitals. So I do have a video, but it's a YouTube video, which means that you're not going to be able to watch it on your computer. So I'm going to have to show it to you when I get back. But just to give you an idea to get started, what you want to do is picture an XYZ axis and pretend the nucleus is at the 0, 0, 0 point on that axis. And then all of the orbitals exist one on top of each other, centered on the nucleus. They all overlap. So as I said, I know that's really hard to picture, but I will show you the video when I get back. Thanks.